Hello, so today we are going to do this problem, which is part of Leetcode Daily Challenge, maximum width of a binary tree. So basically we have a binary tree, we get the root, and what we want is the maximum width of the tree. So what do we mean by maximum width? It means, of course, the maximum width among all levels, so we take the width of a level. Now, what does it mean, a width of a level? Well, basically it's the length between the end nodes. Okay, so basically we take the leftmost non-null node, the rightmost non-null node, and we take the difference between the two positions, and that would be how many nodes are in between those two, and that's the width. With an example, it should be easier to understand. So let's take a look here at this example. So for the first one, well, the width is just one node. For the second one, the width is 2 because there is just these two ends. The difference, they are next to each other. For this one, how many nodes in between the ends? So this is the rightmost one, this is the leftmost one. So we have 1, 2, right? But there is also the null one here. This one is null, but we should count it. So there are 1, 2, 3, 4. So there are 4. The key point here is to know that even though this one is null, we should count it as part of the width, right? Because it's in between the rightmost one and the leftmost one. And so that's 1, 2, 3, 4. Okay? So that's why we return 4 here. And now for this last one, which a little bit more tricky. So for the first one, this is, by the way, sorry, just to clarify here, the max one is this one because it's 4, because this one is 2 and this one is just 1, so the max is 4. Now for this one, still the first one is the width is 1, here the width is 2. Here the width is, there is the nil one here, there is the nil one here, so the width is 4 in this level here. Okay, now for the last level, well, we don't care about this one, right? Because it's after the rightmost non-null node. And so we don't care about that one, but we care about what's in between. So we care about this one. And then here, think about as if you had a node here that has 2 here, right? And similarly, think about as if you had a node here with null. And then that node, if it was working properly, it would have 2 here, right? And so how many we have? Well, we have 1 here, 2, 3, 4, 5, 6, 7. So overall here we have 7. And again, just to clarify, note that we didn't take the 1 here, right? Because it's after the rightmost non-null. Okay. Similarly, if let's say this node didn't exist and we had node here, then we won't count this one. We'll just count from here. Okay. So basically it's the width of between the leftmost non-null and the rightmost non-null. So in this case, as we said, it's 7. So that's the idea. Now how do we solve it? Okay, so how do we tackle this? Well, let me just start with the first thing to know about a binary tree. And so with a binary tree, let's say you have a node here, some kind of node here, and then you have another node, and then you have another node, and this node, and this node, and this node. If we were to just number these nodes, just numerically, then this would be number 1, this would be 2, 3, 4, 5, 6, 7, right? So by definition for a node like this, right, if this node was, if its first child was at some position, let's call it pos, let's say position P, then by definition this one would be a P plus 1 because we just the numeration is just the left one and then the right one, okay? And so by definition, if we were to number it, the left child, the position of the right child would be the position of the left one plus 1. That's just, that just normally because we count in this direction, okay? Now the other thing to think about is a property of binary trees is if this is position for the parent, then you know that the child position is, the left child position is going to be, so let's say a node has position pos, then the left child would be at pos multiplied by 2, And then the right child would be, because the right child is just, as we said here, next to the left child, it's going to be just position multiplied by 2 plus 1. So just this plus 1. This is a property of binary trees. And if you take a look even at this example here, it works because, for example, this one is 1, then this one should be 2 multiplied by 1, and that's true. And this one should be 2 multiplied by 1 plus 1, and that's the case. This one should be 2 multiplied by 2, which is 4. This one should be 2 multiplied by 2 plus 1, which is 5. And this one should be 3 multiplied by 2, which is true here, 6. And this one should be 3 multiplied by 2, 7, right? So even if you number them just manually, you can see that this formula holds. And this is the main idea that we will use to solve this problem, okay? And so you could try to solve it with DFS using this idea, but I'll explain it in using BFS. So let's attempt to solve it with BFS. So what do we want to do? Let's take the first example here and just show you what we want to do. So 3 and then 9. So what we can do with this here is, what do we need? We can just, what we want is to get the rightmost, right? We want to get the rightmost in a level, right? The rightmost node in the level. So actually the rightmost non-null, just to be precise. And then we want to also get the leftmost non-null in a level. Once we have this, what can we do? Let's call this maybe R, and let's call this left. Once we have these, then it's easy. If we have their position, we can just take the right one, the position of the right one, minus the position of the left one, plus 1, and this would be the width of the level, right? By definition, right? It's just the difference. It's just how many nodes are in between the rightmost and the leftmost. So let's just take position of one minus position of the other, and plus 1 here to count for the length. And so since we want the maximum width, we can just go level by level using BFS, right? BFS allows you to go like this, level by level. And for each level, we can calculate the width and then just check if it's the max so far or not. Okay, so what we established here is that if we are able to get the positions for each node, then it's easy to calculate the width and it's easy to get the max with BFS for each level. Okay, so now the only thing remaining to think about is how do we get the position? Well, that's where we come back here. It's easy to have the position. We can just, while we are doing our DFS, we can just check what's the position of the node. Let's call it, so if it's position, then when we add the children of this node, the left child and the right child, when we add them to our level list that we traverse BFS with, then we can just say, basically, when we add for the node that left, we will say its position is going to be exactly what this is said here, which is position multiplied by 2. And then for the right child, when we add it, it's going to be node dot right position multiplied by 2 plus 1. Okay, this way we actually shouldn't add. If the node dot left doesn't exist or node dot right doesn't exist, we don't add them because we don't need them. We just need the non-null nodes, right? Because we are looking for the rightmost non-null and the leftmost non-null. And so, for example, for 2, we won't add its left child because it's null. We'll just add its right child. Okay. And so how would this work, for example, here? So for this example, let's call best the maximum width we have. So initially, let's just initialize it to 0. And so first, our level is going to be, for BFS, we can just go level by level. And each time we traverse a level, we put in another array, let's call it next. We put the next level, so with that, we traverse it in the next layer, right? And so here, we go here, it's 1. First, our level just has the node 1. And so the node 1, of course, what's the position of node 1? We want to add both the node and this position so we can calculate the width. So initially the position is 0, right? And so we go through the node and we check how do we get the rightmost and the leftmost in a level? Well, let's say a level you have a couple of nodes, maybe node 1, node 2, all the way to node k. how do you get the rightmost one? We will add in our level, remember, only the non-null nodes. And so we know by definition, because we add in order, we add in the right order, right? We traverse this one, we add it, and then we first traverse the children of this one, then the children of this one. And so the last one would be actually the rightmost one. And then this one would be the leftmost one. What this will tell us is basically to get the rightmost one, R is just going to be the level node at position 0. Sorry, this is left. Is going to be the one at position 0, and the right one is going to be the one in the last position. In Python, we can do -1. And so it's easy to get which one is the rightmost, which one is the leftmost. And since we use a tuple here where the first position is the node itself, so think about this as the node, and then this one would be the position. And so to get the position, we can just do at position 1, and then here at position 1 will give us the position, and this way we can calculate the width. Okay? And so let's use this formula then here. So here I'm representing this as node and this as position. And so for 1, we want to go and check if it has a left child. It does have a left child, and so we are going to add it to next. Now, what is its position? Well, its position is the position of the node multiplied by 2. Okay? And so here, since the position it was initially 0, we will have 0, which is a little bit not ideal. So if you want to change that, you could start from position 1. Okay? If you want to change that, you could start from position 1 here, up to you. Okay, so here the position would be 0, position multiplied by 2. So in this case, it would be 0. It's not bad. It's a little bit, I agree, it's a little bit strange that we have 0, 0 here, but it's not bad because for the other cases, it would be different. Now the left child is 2. What would be its position? Well, position multiplied by 2 plus 1, so its position is 1. Okay, and then now once we traverse all the nodes in this level, we add their children, we are going to copy this one in the level. And so now this one, then we copy it, is going to contain 3, 0, and then 2, 1. Okay, and now our next is empty, and we need to update best. We update it using this width here. So what's the rightmost one? Well, the rightmost one is this one. What's the leftmost one? It's this one. What are the positions? It's 1 minus 0 plus 1. So it's 2. And this is the right answer for this level, right? Because it has 1 and 2, and the difference between them is just, the width between them is just 2, right? Okay, so now we traverse this with normal BFS. So we start with the first node, 3. What's its left child? Well, its left child is just 5. Now what's the position there? Okay, well, the position is still going to be position multiplied by the position multiplied by 2, so it's going to be 0. Now what's the position of its right child? So its right child is 3, and its position is going to be 1. Now what's so we finished this one, we go traverse this one. What's its left child? It doesn't have any left child, so we don't add it. It has a right child. It's 9. What is the position for the right child? It's position multiplied by 2 plus 1. So it's 2 multiplied by, so it's 1 multiplied by 2 plus 1. So it's 3. Okay. And so now again, we copy this thing here. Just normal BFS. So we have 5, 0, 3, 1, 9, 3. Then this one becomes empty, and now we need to update our best. Now what's the leftmost child and the rightmost child? Well, the leftmost is just 1 at position 0, the rightmost is 1 at position 1, so it's this one and this one. Now what are the difference between the positions? It's 3 minus 0 plus 1, which is 4. Okay, and so now when we go traverse these, each of their children left and right would be null, and so we'll end up with next being empty, and so we'll exit our while loop for BFS, and this is our best answer, right? You could try to run this on an example where this is not, the last child is not the rightmost one, and you'll see it will still work. Yes, and so that's pretty much the idea here, is using this position formula and using this fact about binary trees, and then just running BFS, normal BFS, it should solve it. Now, what's the time complexity? Well, BFS is O of E plus V, which is number of edges plus number of vertices. So overall, it should be just the number of nodes in the tree. So it's O of N here. Yeah, and that's pretty much it. Now let's code it up and make sure it passes our test cases. Okay, so let's implement this solution. So first we need, the first thing we need is level for our BFS. And so we'll start with the root node. And this is basically just the position. And now we start with the best width so far is 0, and then we'll just return it at the end. And now we'll go through the current level, and we'll add the next level in this list, just like we did in the overview. But before that, for each level, we want to calculate the best so far, just in case the best width is the width of this level, just in case, okay? And so we'll just do max of best. Now, what's the width we said of this level? Well, we said it's the rightmost node, which is the last element in the level. And then we want to get its position, which is at position 1 in the tuple here. So it's, and then minus the, so this is the rightmost node, right? What's the leftmost node in the level? Well, it's the one in position 0. And so we'll take its position. And then we do +1, and so this will give us the position of the rightmost non-null node minus the position of the leftmost non-null node +1, okay? And that should give us the width of this level. And now that we have that, we can just traverse the level and add the children to this next list. And so we get in each position, we get the node end position in level, and then we are going to check if it has a left child. We want to add it. Remember, we add only non-null nodes because those are the only ones we are interested in. And so then we add appended to node.left, and the left child, the position is going to be just position multiplied by 2. Otherwise, for the right child, the position is going to be +1. And then we want to copy, for the next iteration, we want to copy the new levels nodes into the current level. Okay, and now we can just run this. Looks like there is a slight error there. So this should work. Yeah, sorry, we should add node dot right here. Okay, looks good. Let's submit, and that passed. Okay, so actually just one thing I want to show you here, just to make sure this is really clear. So let's just print the positions for each level. So the positions would be just at position 1 for each level. Okay, and so if we do that, then we can see it's 0 for the first level, 0, 1 for the second level, and then 0, 1, 3 for the last level. Now, I know this 0 may be confusing a little bit, so you could change the position here to 1, basically so that you don't end up with the first element always being 0. Now with that, our solution will still work because the difference will still be the same. The width calculation will still be the same. But I think the numbering will be more intuitive here. So if we do that, you can see the first node is 1, then in the next level is 2, 3, and then 4, 5, 7. So it's like, it's more intuitive because 1, 2, 3, 4, 5, 7, so the numbering is ordered properly. And so, yeah, just want to mention this in case this is more intuitive to you. This still works in the same way like before. If we submit, it still works, okay? And so, yeah, if you prefer to start numbering from 1, you could also use that. Yeah, so that's pretty much it for this problem. Please like and subscribe, and see you on the next one. Bye.